Okay, let's continue on the normal distribution. I'm going to concentrate on the special application of the normal distribution. It's called a central limit theorem. Okay, so central limit theorem tells us that for a population with any distribution, the distribution of the sample means approaches the normal distribution as the sample size increases. This procedure in section forms the foundation for estimating the population parameters and the hypothesis testings. Estimating population parameter, that's from chapter 7. We'll concentrate on that. Hypothesis testing, it's on chapter 8. So central limit theorem provides foundation for chapter 7, chapter 8. So central limit theorem itself, the given condition is the random variable x has a distribution with a mean mu and standard deviation sigma. Okay. And the simple random sample of all size n are selected from the population. The samples are selected such that all possible samples of sample same size n have the same chance of being selected. That's basically the definition of the simple random samples. And those two are given condition. And the conclusion is the distributions of the sample means when you pick the sample, each sample will yield a sample mean. Use x bar to represent the sample mean. The distribution of the sample means, of all the sample means, you're going to have a lot of sample means. As the sample size increases, approaches the normal distribution. With the mean of all the sample means, we use mean of all the sample means, population mean, mu, with all the sample means. It's the same thing as the actual population mean, mu. And the standard deviation of the sample means, using sigma of all the sample means equal population standard deviation over square root of sample size. So those two are the most important discovery from the central limit theorem. And practical rules in order to use the central limit theorem, either one of these conditions must be satisfied. You see LT to represent the central limit theorem. If the sample size larger than 30, the distribution of the sample means could be approximated reasonably well by a normal distribution. So when the sample size greater than 30, we can use central limit theorem. And as the sample size becomes larger, the approximation becomes much better, which is closer to the normal distribution. Sample size gets larger, the better it is. Okay, if the original population is normally distributed, then the sample will inherit that particular trait from the population. The sample becomes normally distributed. And for any sample size n, the sample means will be normally distributed. Okay. So either one of these satisfied, then we can use the central limit theorem. So the mean of the sample means becomes population mean mu. The standard deviation of the sample means equal to population standard deviations divided by the square root of sample size. We also call it standard error. Standard deviation is same term as standard error. And this is how when the sample gets larger, how the distribution of the population look like. As we process from sample size equal to 1 all the way to 50, as you can see, the distribution here look like this for the first. So fairly flat. When the sample size becomes 10, then it becomes slightly better. And when the sample size becomes 50, we get a much better, much better approximation. We get a better shape of the normal curve or bell curve. So the bigger the sample size, the better the approximation is. So as the sample size increases, the sampling distribution of the sample means approaches normal distribution. So picking a sample from the population, picking the samples from the population is called a sampling distribution. This process is called a sampling distribution. If you want to use a combination to represent this process, sample size we know is small lowercase n, population size is uppercase N. So basically this process is a combination. We do capital letter N, CR. Okay, so look at this. This determine how many samples we can generate from the population with the size N. And let's take a look at an example. And before we move on to that, so central limit theorem. So the z-score equal to sample mean minus population mean mu over standard deviation, which is sigma over square root n. This is the most important thing. Okay. To summarize what the central limit theorem is, basically that's what it is. Now let's take a look at an example about the elevators. Suppose an elevator has a maximum capacity of 16 passengers with a total weight of 2,500 pounds. That means, on average, each passenger should be 2,500 pounds dividing by 16. You get an average weight for those 16 men. So it'll be 2,500 by 16. And then put it into the calculator, get the result 156.25 pounds per person. Assuming worst case scenario in which the passenger are all male, what are the chances the elevator is overloaded? So if the total weight is above 2,500 pounds, that's overweight. So assuming male weights follow a normal distribution with population mean mu, a given population mean mu equal 182.9. We also know the population standard deviation 40.8. Find the probability that one randomly selected male has a weight greater than 156.25. So since you only pick one male, so we use a regular z-score formula to find out the probability here. And right here for part B, you have a sample of 16 males. To do that, you have a sampling distribution. Now we use a formula for the central limit theorem. So z-score equal to population sample mean minus population mean mu over population standard deviation over square root of sample size. Okay. So if you look at this, if a sample of 16 males have a mean weight of greater than 156.25 pounds, which puts the total weight at 25,000 pounds, exceeding the maximum capacity, so which create risk for those passengers. Now find the probability that one randomly selected male has a weight greater than 156.25. So you draw the bell curve, and you're looking for the area to the right because greater than keyword. So looking for area to right, to the right. Draw the bell curve, visualize this, we're looking for the area to the right here. Now again, find the z-score first. X equal to 6.25 equals here. And then mu is 182.9. Find the difference over the population standard deviation, 40.8. You get a z-score which is negative 0.65, approximately equal to. Okay. Now you go to the table A2. So we go to the table A2 here, look for negative 0.65, then go back to the first page. Then use negative 0.6 and 5. They have intercept. Intercept turned out to be 0.2578. 0.2578, that's the intercept. And that's what we're looking for. Okay. We'll go back 0.2578. This is 0.2578. Area to left is 0.2578, but we want area to right, so this is equal to 1 minus 0.2578. Then we get 0.7422, which means we get a 74.22% of chance with probability. If you pick one randomly selected male, his weight will be greater than 156.25. Now find the probability that a sample of 16 males have an average weight greater than 156.25. Since the distribution of a male, since the population is normally distributed, right? It says here. Since the population is normally distributed, so the sample inherit the population property, so sample means are normally distributed. Population is normally distributed, so the sample inherited the property from the population, so the sample means are normally distributed. Then we're going to apply the central limit theorem here. So the essence of the central limit theorem is z-score equal to sample mean minus population mean mu over population standard deviation over the square root of sample size. So the mean of all the sample means equal to population mean, 182.9, and then standard deviation of all the sample means equal population standard deviation over the square root of sample size. So it's 40.8 over square root of 16. Square root of 16 equal to 4. So this 40.8 by 4, 10.2. Okay, now you apply the central limit theorem here. Then plug in the sample mean. Yep, so sample mean minus population mean over square root of over the standard deviation for the sample means, we get a z-score of -2.61. And again, if you go back to the table A2, -2.61, the probability -2.61. Probably turn out to be 0.0045. So that's area to the left. You get it. -2.61, 0.0045. Now let's go back to the question. That means area on this side is 0.0045. So the area on the right will be 0.9955. That means the probability for average weight greater than 156.25 equal to 1 minus 0.0045 9955. That means this chance is a lot higher, which almost like 100%. So while there is a 0.7432 probability that any given male will weigh more than 156.25 pounds, there's a 0.9955 probability that with a sample of 16 males of an average weight of 156.25 pounds or greater. So if elevators fail to composite with all males, there's a very good chance this safe weight composite of 2,500 pounds will be exceeded, which is very risky. So you should definitely avoid that. So now, another example, given the population of men has normally distributed weights with a mean of 172 pounds, standard deviation of 29 pounds. If one man is randomly selected, so that means we do not have central limit theorem apply here, means 172, and this weight is greater than 167 pounds, given x value equal to 167. So now this is on the left, so x equal 167, and we're looking for the area greater than, meaning area to the right. Again, first of all, we find the z-score using x minus mu over sigma, 167 minus 172 over 29, using -5 over 29. Let's see what that is, -5 over 20. This is -0.17, approximately. And again, go back to the table A2, look for the area to the left. So again, first page of the table A2, -0.17, we get a probability of 0.4325. Okay, so that's area to the left. If you go back, area to the left is 0.4325. 4325. We're looking for the area to the right. So probability for x greater than 167 pound equal to 1 minus 0.4325. This is 0.5675. That means probability here will be 56.75%. Now, probably, if given the population, man has normally distributed with the mean, still population mean mu equals 172, standard deviation is 29. So now we have 12 different mans are normally distributed. 12 different men randomly selected. So we get a sample mean. We compare the sample mean to population mean. So this is what we call a sampling distribution. We are comparing the sample mean to the population mean. Again, draw the bell curve. Population mean mu is 172. Sample mean 167. Greater than that. So again, we're looking for the area to the right. Now using the central limit theorem, we have sample size which is 12. The sample mean is 167. Because this average weight, mean weight. So using central limit theorem, find the z-score x bar minus mu over population standard deviation over square root of sample size. 167 minus 172. Okay, dividing by 29 over radical of 12. Then we're going to get a much smaller z-score. Let's turn out to be negative 0.60. Okay. Now again, you go to the center of the table A2. Look for the probability. 0.60. It's right here. 0.2743. So that's associated probability. 0.2743. Area to the left is 0.2743. Look for the area to the right. So probability for sample mean greater than 167 pound equal to 1 minus 0.2743, which is 0.7257. So this probability is a lot higher, meaning we have a much better chance. For 12 different men, the average weight is greater than 167 pounds. Have much higher chance.